All right, hello there. This is Probability and Statistics, day number 7 on the binomial distribution. So a binomial distribution is an example of a discrete random variable where the number of possible outcomes is 2. So for example, you could win or lose, a yes or a no, a heads or a tails, and anything else to that context. Okay, outcomes of a binomial distribution are mutually exclusive, meaning you can't win and lose at the same time, get a yes and a no, or a heads and a tails. And what this means is that the probability of A and B equals 0. Now, since we have 2 possible outcomes, you'll have a probability of each of the outcomes, and you decide based on the context of the problem whether outcome number 1 is success or failure, and outcome number 2 is success or failure. Typically, we refer to the probability of the first outcome or success as P and of failure Q. And of course, these 2 possible outcomes, the probabilities of those 2 add to 1. So let's get into a quick review example on the idea of a discrete random variable, and then we'll get right into a few examples with binomials. All right, so this is very similar to an exam problem given a number of years ago. And this review example goes over this idea of the discrete random variable. Of course, the discrete random variable has discrete, distinct outcomes, right? So for example, here, our possible outcomes are 0, 1, 2, 3, all the way up to, looks like, headed off to infinity. So if the probability distribution of a discrete random variable x, where x as known is to be 0, 1, 2, 3, all the way up to infinity, or as high as we want it to be, is given by the following. Okay, we want to find the value of m if the probability that x equals any individual x is m times 1/7 to the x. Now I'll give you a hint, and that is that there is a geometric series hidden here. So let's consider for a moment all of these possible outcomes and their probabilities. So let's take probability that our discrete random variable equals 0, plus the probability that our discrete random variable equals 1, plus 2, and let's just send it off to infinity. Right, well, we know that this, based on the definition of a discrete random variable, should equal 1. Well, let's take the context of this problem and let's build each of the first 3 probabilities and see if we can come up with some kind of pattern. Okay, so based on this discrete random variable's probability distribution function, right, this thing, we can say that the probability that x equals 0 would be m times 1/7 to the x power, which is 0. Okay, let's find the probability that x equals 1. Well, that would be m times 1/7 to the first. 2 would be m times 1/7 to the second, and we would continue this. If we went up to the nth power, let's go yellow for that, that would be m times 1/7 to the nth power. And of course, the sum of these, we're going to send n to infinity. So n will go to infinity since we don't know the number of possible outcomes. Okay, so what I'm going to do is I'm going to factor out an m, because that's what I'm seeking, right? So I'm going to take out an m. That leaves me with 1/7 to the 0 plus 1/7 to the first plus 1/7 to the second. And I'm just going to keep on keeping on there. Okay, so my hint to you above was think geometric series. Okay, well, if I look at an infinite geometric series, the only way that this infinite geometric series, which we've seen a formula for this, a over 1 minus r. The only way that this can converge to a finite value is if r is between 1 and negative 1. Right? It looks like to me, right, I get this series, and I go from, let's say, n equals 0 up to infinity of 1/7 to the nth power, right? That would give me exactly what we have here, which would be 1/7 to the 0, 1/7 to the first, 1/7 to the second, etc. So I have identified that r equals 1/7. I just have to identify what a equals. So a would equal the first term. When I isolate that first term, a ends up equaling 1. Therefore, this sum would be equal to 1 over 1 minus 1/7, which is the same as 1 over 6/7, which would be equal to 7/6. So this summation right here is equal to 7/6. Thus, I can say that m times 7/6 is equal to 1, and therefore m must equal 6 over 7. Okay, that's an interesting one, right? And kind of ties in the idea of geometric series. All right, let's go ahead and look at a few problems on the binomial distribution. Okay, so a binomial distribution is built using the following, and I'll explain what all of this stuff is. So the probability that x, our variable, equals any of its given possible outcomes, right? So this x is a specific outcome. This x is our random variable. Okay. How this is built is this notation here actually is equivalent to ncx. This will be the probability of success to the x power. This is the probability of failure to the n minus x power. Okay, where n is the number of trials, x is the number of successes, p is the probability of success, and q is the probability of failure. So let's make sense of this in the context of an actual problem. Okay, a die is rolled 6 times. Okay, that right there tells me that n equals 6. What is the probability of rolling a 4? Okay, so the probability of rolling a 4, okay, is going to be, of course, 1/6. So p is 1/6. Thus, q is 5/6. Okay, and of course here I want x to be 3 times. So success is rolling a 4. The number of times I want to roll a 4 is 3 times. Okay, so we'll look at less than 2 times here in a moment. So we're going to calculate this without a calculator first, then with a calculator second. So we're saying that the discrete random variable x is binomial with 6 trials, and the probability of success is 1/6. Okay, this is how you write out, like in shorthand math notation, that a discrete random variable is binomial. You start with the letter representing the discrete random variable, the distribution, which is binomial, the number of trials, which is 6, or n, and the probability of success, which is p. That implies a lot of information going on here. So this will denote the number of 4s rolled. So without a calculator, define the probability that x equals 3. Okay, that will be 6, choose 3. Probability of success is 1/6 to the 3rd power. Probability of failure, 5/6 to the 6 minus 3. Okay, so we could go ahead and calculate that. I'm not going to. I'm actually use my calculator in a moment to do that, but you would expand that and work that all out. Okay, let's look at less than 2 times. Okay, less than 2 times. So the probability that x is less than 2 is equivalent to the probability that x is equal to 0. So 0 fours plus the probability of 1 4. Okay, another way you could look at this would be the probability 1 minus the probability that x is greater than or equal to 2. But that would take you a longer time, right? A lot more writing and all that stuff. So let's go ahead and write this out. Okay, so my first expression here would be 6c0, 1/6 to the 0, 5/6 to the 6th. Okay, plus 6c1, oops, 6c1, 1/6 to the 1st, 5/6 to the 5th. Okay, and of course that would yield you a value as well. All right, we're going to calculate those in a minute with our calculator. Okay, so how do you find an actual probability using your calculator? Well, it depends on, you know, how many probabilities you're trying to find. So for example, right, I just want one specific possible outcome. So if that's the case, what you use on your calculator is this distribution called Binomial Cdf. PDF will find you a single possible probability. So take your calculator and you'll see the button, the vars button. What I want you to do is press second vars and go up. By going up, I mean you're looping back to the bottom. And option A is called Binomial PDF. Okay, Binomial PDF asks you for the number of trials n, so we're going to put a 6. Then it asks for the probability of success, which is 1/6. Okay, so that'd be P, which is 1/6. Then what you want is the X value. The X value that we want is the number of successes, which is X, which we would say 3. You paste it, you get an answer, and it looks like these two answers would be the same, which would be 0.053 and a 6. So a little over 5% chance that you roll exactly 3 4s. Okay, so when working with some interval or a less than or greater than, less than or equal to, greater than or equal to, where you might have multiple probabilities, either you could find both of those probabilities using a PDF and add them together, or you can do what's called a CDF, okay, which accumulates probabilities. So the probability that x is less than 2 would be a binomial CDF. I should use the notation right, binomial CDF. And very similarly, press second vars, go to option B, right below PDF, you'll find CDF. Number of trials would be 6. Probability of success would be 1/6. And the X value that I'm going to put in here is the last X value that I want to accumulate up to. So I want to accumulate 0 and 1. I don't want to accumulate 2 unless it was less than or equal to 2. So I want to go and put a 1 right there. So again, N and P and your X value. Okay, so binomial CDF, 6, 1/6, and 1. Oops, and 1 comes out to be 0.737. So a little over 73%, almost 74. Okay, let's go ahead and look at the next example. All right, here we go. Calculator, okay. Let the discrete random variable x be binomial with n number of trials and p is a success. Represent the number of heads obtained when Tommy flips a coin 10 times. Okay, so this is going to be binomial. So x represents the number of heads Tommy flips. It'll be binomial. We're expecting 10 flips, and the probability of success is half. Right, when you flip a coin, you get a 50-50 shot. If Tommy is attempting to find the probability that he flips more than 7 heads, okay, find each of the following. Okay, so first of all, n we know is 10, p 1/2, q also 1/2. So the probability that x is greater than 7, we could find the probability that x is equal to 8 plus the probability that x is equal to 9 plus the probability that x is equal to 10. Now this would be a rookie mistake, and I wouldn't do that. I would actually use a CDF. There's my fancy x. Okay, I would take 1 minus the probability that x is less than or equal to 7, right? Because that would accumulate those values above it, right? Because we know that the probability of each of these 10 possible outcomes should add up to 1. So I'm going to take and do 1 minus a binomial CDF at 10, 1/2, and 7. Let's figure out what that equals. 1 minus binomial CDF, 10, 0.5, and 7. Now we want to include 7 because we want to know the probability that x is less than or equal to 7 and take that away from 1. It looks like I end up getting 0.0547, so about 5.5%. Now let's make sense of this, right? If you think about flipping heads, the expected number of heads flipped in 10 tosses should be 5, right? 50-50 chance. Your expected value, and this brings up a really good point. The expected value of a binomial is just n times p, right? So in this case, that would be 10 times a half. So if we're curious about the probability of flipping 8, 9, or 10 heads, like clearly that's not going to be likely at all, right? Flipping 10 heads, very unlikely. Flipping 9 heads, a little bit more likely, but still unlikely. And 8, of course, it'll start to, you kind of get this distribution, like here would be 0 and 1 and 2 and 3 and 4, and of course 5 is the expected value, and then you'd see a symmetrical balance on the other side as well. Not likely to get 0, not likely to get 10, very likely to get 5. So that's the binomial distribution when you've got a probability of success at 1/2. Let's continue with another example. Okay, a manufacturer finds that 30% of items produced from one of the assembly lines are defective. During a floor inspection, the manufacturer selects 6 items. So let's identify a couple of items here real quick. 6 is going to be our n value. I'm guessing 0.3 is going to be our p value. So that'll mean q is equal to 0.7. Okay, find the probability that 2 are defective. Now that confirms it. Right, defective is considered success because that's what I'm looking for. Okay, so the probability, and I'm going to define a new random variable, y. Okay, and I'm going to say that y is binomial 6 trials and 0.3 is success. And that'll represent the number of defectives in a floor inspection. Okay, so since I've defined the variable now I can work with finding probabilities. It just helps me shorthand things. Okay, so the probability that y equals 2 will be 6 choose 2, 0.3 to the 2, 0.7 to the 4. That's how I would do this if I were to lay it out fully using that binomial setup. Or I could do a binomial PDF, right? PDF because I'm just looking for the probability of one possible outcome. I would go 6, I would go 0.3, and of course I would go 2. So let's see what that comes out to be, and then we'll look at the part B. So I go to my binomial PDF, I go 6, 0.3, and 2, and I come out with 0.324, so about a 32% chance. All right, that's a 324. Okay, part B, very similar to some of the other problems. Probably there are more than 2 and less than 6 defectives. Okay, so this would be the probability that y is greater than 2 and less than 6. Okay, this is interesting. All right, I'm going to find this probability by subtracting 2 CDFs. So I'm going to take a CDF accumulating from 0 to 5, and I'm going to subtract a CDF accumulating from 0 to 2. What that'll give me is the probability that y equals 3 plus the probability y equals 4 plus the probability that y equals 5. And my answer comes out to be 0.255. All right, let's continue to the next slide. Okay, a couple binomial properties. First of all, we did speak about this earlier. The expected value of a binomial is actually equal to mu, which is equal to n times p, so number of trials times probability of success. The mode of the discrete random variable is the occurrence with the largest probability. Okay, and the variance, which is sigma squared, is n times p times q, or n times p times 1 minus p. Okay, so let's take a look at this example. A jar contains 7 marbles, of which 2 are green. A marble is selected, color noted, and then replaced. This is done 50 times. Okay, so A, the mean number of green marbles selected. Okay, so in this case, P is equal to the probability of success here. Green marbles, there are 2 out of 7, so P will equal 2/7. So the expected value, which would be mu, which I would call the expected value of this particular distribution. If I were to define X as binomial 7 and let's say, oops, I'm sorry, wrong, 50, and probability of drawing a green would be 2/7. That would be our binomial distribution representing the number of green marbles selected in 50 trials. That would be n, which is 50 trials times 2/7. So the expected number of green marbles would be 100/7, even though that's not an actual number. Well, an actual attainable number, seeing that that would not be a whole number. We can still get an expected value that's not an attainable number. It just gives us an idea of approximately how many green marbles we should end up with. Okay, B, the standard deviation of the number of green marbles. Okay, so the variance, let's find that first. Sigma squared will be, of course, the value of n times p times q. So that's 50 times 2/7 times q, which is 5/7. Okay, so the variance will be, oh gosh, what is that? 10, it's 500 over 49. Therefore, the standard deviation would be the square root of 500 over 7, right? Because standard deviation is the square root of the variance. Okay, you could simplify that if you wanted to and go with a, what would that be, 10 root 5 over 7? That would be the standard deviation of the number of green marbles selected. Okay, let's get to our last example. Okay, a couple of other important properties that you might see. These happen here when, for example, you're taking the expected value of multiple potential discrete random variables. Could be binomials, could be otherwise. Okay, so take a look at those, work through those. On your free time, you'll see a couple of those in the homework. Okay, example given here. Okay, a discrete random variable y has its probability distribution function given below. Okay, so we can see that there are 4 possible outcomes: -2, -1, 0, and 1. Part A asks for finding k. Well, we know that each of the probabilities summed. Okay, if I add those probabilities up, the sum of them should be 1. So I get 4k plus 0.6 is equal to 1. Therefore, 4k is equal to 0.4. Thus, k is equal to 0.1. Now, I'm going to go ahead and put these in here. So I have those to reference in a moment here. Okay, part B says that a given function f is defined as f of y is actually equal to the probability that y is less than or equal to y. So what does that mean? Okay, so for example, part I, f of -1 is really just saying what's the probability that y is less than or equal to -1. Well, in our case here, that would be these two probabilities. All right, and I sum those two together, and it looks like then f at -1 would be 0.3. Okay, part 2, f at 1 would be the probability that y is less than or equal to +1. Well, +1 is the maximum possible value, so I'm just going to add all 4 of them up, and of course this would equal 1. Okay, part C. Part C says find the expected value of y. Okay, so let's lay it out here. Since this is not binomial, I can't just take n times p because, well, clearly this is not the same scenario. So expected value of y is always the y value, right? The sum of the, let's go from I equals 1 up to, actually we'll go, in this case, I equals -2 up to 1, okay, of y sub I times probability of y sub I. So it's just the sum of each of the y values times their probabilities. So the first would be -2 times 0.1, the second, -1 times 0.2, the third, 0 times 0.3, and the fourth, 1 times 0.4. Okay, so the expected value of y comes out to be -0.2 plus a -0.2 plus a 0 plus a 0.4. If I add those up, it looks like I get 0. So the expected value of y is actually 0. That's pretty interesting. Okay, that was part I of part C. Let's find the variance. Okay, so the variance of y, this is going back a few lessons, is going to be equal to the expected value of x squared minus the expected, and it shouldn't be an x squared, this should be a y squared. Getting tired, guys, getting tired. Minus the expected value of y, quantity squared. Now I already know this value. Right, that value is 0, so that'll be pretty easy to work with. So this will just actually be equal to the expected value of y squared. Okay, so how do I find the expected value of y squared? Well, I take each of these values and I square them. And then I do the same thing as I did for the expected value of y. So instead of -2 times 0.1, I'm going to take -2 squared times 0.1 plus -1 squared times 0.2 plus 0 squared times 0.3 plus 1 squared times 0.4. Okay, that comes out to be 0.4, 0.2, 0, and 0.4. So the expected value of y squared ends up being 1. All right, there you go, guys. It's a little bit with binomials as well as a little bit more with the discrete random variable. See you in the next video.